Hello everyone. Today we'll be solving the problem subsequences, right? So this was asked on where did it go? Testing round 1 2. Testing round 1 2, right? So basically you can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So what the question states here, we are given an array of n distinct integers. So just give me a second, 1 second, 1 second. Yeah, we are given an array of n distinct integers and a number k. We are given a array of n distinct integers and a number k. We need to count how many increasing subsequences of length exactly k plus 1 exists, right? So we need to count how many increasing subsequences of length exactly k plus 1 exists. Exactly k plus 1 exists, right? So just keep this in mind. Again, I'll just read this one out loud. We are given an n distinct integers and a number k. N distinct integers and a number k and a number k. We need to count how many increasing subsequence of length exactly k plus 1 exists, right? So just give me a second. So here again we need to count how many increasing subsequences of length exactly k plus 1 exist, right? So each subsequence should have strictly increasing elements and order must be preserved from the original array. So each subsequence should be strictly increasing elements, right? Should have strictly increasing elements. Again, I'm repeating this one. Just keep this in mind. Each subsequence should have strictly increasing elements and order must be preserved from the original array, right? So the array elements ranges from 0 1 to n. The array elements range from 1 to n and all are distinct. The array elements range from 1 to n and all are distinct. So output, what can we expect? Basically count of all the valid increasing subsequences of length k plus 1, right? So the output has to be count of all the valid increasing subsequences of length k plus 1, right? So this is the question. Mainly the first two lines is the main part here. We are given an array of n distinct integers and a number k. So we need to count how many increasing subsequences of length exactly k plus 1 exist, right? How many increasing subsequences of length exactly k plus 1 exist, right? So I hope the question is completely clear, man. Let's do one thing. So let me delete this one entirely. So yeah, let me come to the input output part. This 5 to whatever they have given here. So n is nothing but 5. We have been given n different elements, right? So as I've said, n different elements. So this one is nothing but 5. N is nothing but different. This one and k. So I said in the question that we have been given array of n distinct integers and number k, right? So the number k is nothing but here this one 2. And array and the array they have given array of numbers we have been given here this one 1 2 3 4 5 1 2 3 4 5 or 1 2 3 5 4 actually 1 2 3 5 4. So the output that we need to get here is 7. So how we got the output 7, that we will discuss in approach step by step, right? So for now I hope the input output part along with the question is completely clear. Let's do one thing. Let's discuss the approach part followed by the complexities and then let's write the code as usual. Let's discuss the approach first. So here I have considered the same first example that they have given in the question, right? So n we have been given 5, k we have been given this one 2, and this is the array 1 2 3 4 5. The output that we need to get here is 7 as we had discussed in the input output part. So let's move on with the step by step explanation here. So same input we are considering here, right? So first what we'll do, we need to count the number of increasing subsequences. Basically before moving on with this one step by step explanation, I just want to tell you that we will be making use of the segment tree. We'll be going with the segment tree and the DP, dynamic programming, right? So we'll be going with the segment tree along with the dynamic programming. Previously we had solved lazy segment tree, segment tree with the lazy propagation along with the bit manipulation, right? So today we are going with a segment tree along with the DP, nothing but dynamic programming, right? So here let's move on with the step-by-step explanation. Just keep that in mind that the approach that will be going with us segment tree, right? So this will be the last problem on the segment tree. Next, we will be solving on the Fenwick tree or BIT, nothing but the binary index tree, right? So these two, basically we'll finish it off these two, and I have opted this one as well, sparse table as well within the this one table, right? So within this playlist, so we are solving 6 problems on segment tree, 6 problems on the Fenwick tree, and the last 3 problems it will be on the sparse table, right? So now, yeah, let's move on with the step-by-step explanation, right? So we need to count the number of increasing subsequences of length, nothing but in the question itself they have mentioned k plus 1. So k we have been given 2 in the input, and accordingly with the first input that we have considered, k plus 1 would be 2 plus 1 3. So I hope this part is clear, man, easy to understand, right? So next, let's go with the coordinate compression as we are making use of the segment tree. So as we are making use of the segment tree, so coordinate compression in the sense, so we will be for this particular problem, in the segment tree, we will be going with the 2 methods, nothing but query and update. Query and update, right? So here let's go with the first step, nothing but the coordinate compression means the value we are pointing to the array here. Value we are pointing to the array. And one more thing, array is zero based indexing. We have considered zero based indexing for the array, not one based indexing. So 1 is pointing to the zeroth, this one, nothing but 0, 2 1, this one 3 2, this one 4 3, and 5 4, nothing but here in the array we have been given this one, what do we call, 1 2 3 5 4, not 1 2 3 4 5, right? So indexing would be, the compressed array would be 0 1 2 4 3, not 0 1 2 3 4 here, because in the array we have been given 1 2 3 4 5 4, not 1 2 3 4 5, right? So the last two numbers differs, 1 2 3 5 4, not 4 5. So the compressed array would be here when we point out to the array. So this will be 0 1 2 4 3, not 0 1 2 3 4, right? So we are done with the this one coordinate compression, right? So now we got the compressed array. This was easy, man, this was easy. We are just compressing the, we are just going with the part coordinate compression, right? So we are done with this. Next, as I have said, we'll be going with the DP as well, right? So along with the segment tree, we have went with the we'll be going with the DP as well. One more thing, so when we started the problems on segment tree, initially we started with only segment tree, then we have solved the segment tree with the greedy as well as the binary uplifting or the binary lifting, right? So that is one thing. Next one, we went with a lazy segment tree or the segment tree with a lazy propagation, only lazy segment tree. Then we went with lazy segment tree along with bit manipulation, right? Now the last problem, we are going with a lazy only segment tree with a DP or the dynamic programming, right? So I hope this part is clear, right? So we are trying to solve every approach, every combination of approaches basically, right? So that's what I'm doing basically. Now let's move on with the step 2 here. We'll, as I have said, we'll be making use of the DP, right? So we use DP of length 1, nothing but the number of subsequences. We need to find the number of subsequences, right? So here of length plus 1 ending at the index I, ending at the index I. Initially, see here, I have just written DP of 0 I equals 1 for all the I, right? So since each element forms one length subsequences, each of the element forms one length subsequence for sure, right? Each element forms one length subsequence for sure. So DP of 0, we are giving 1 1 1 1 1 because in the input we have 1 2 3 5 4, right? 5 elements we have. So in that 5 element spot, in that spot, what we are saving, 1 triple 1, this one 5 times 1, basically you can just directly consider 5 times 1 means since each element forms one length subsequence at least, so we will be initially going with DP of 0 is nothing but triple 1 double 1, right? So I hope this is clear, easy to understand. Next, let's move on with the next step, nothing but we went with the initialization of the DP. Next we will be seeing the build process using the DP. So what we will do, we will build the DP for subsequences of length 2, subsequences of length 2. Initially what it is, a DP of 0 consists of 5 times 1, right? 5 times 1. So now let's build for the subsequences of length 2. length 2. Strictly I have written here length 2, right? So we will be making use of the segment tree along with the DP to maintain the prefix sums of DP of 0j for j less than I. That is the reason we'll be going with the segment tree here. Along with the DP, we'll be making use of the segment tree for what reason? To maintain the prefix sum reason. So for the prefix sum, for the calculation of prefix sums itself, will be mainly going with the segment tree. We'll opt the segment tree mainly for the prefix sum calculation, as we can solve the problem with the time complexity big of logarithmic n per query, right? So that is the reason mainly we make use of the segment tree and this one Fenwick tree as well. Fenwick tree and yeah, segment tree and the Fenwick tree. Sparse table is quite different, so we will be discussing later when we solve the problems on the sparse table. So segment tree and the Fenwick tree or the BIT, basically we opt that data structure particularly because we want to solve the problem, or we want to calculate the prefix sums initially, and or we need to solve the problem with the time complexity when the time constraint is tight, right? So when the constraints are tight, basically when the constraints are tight, basically which will be of basically when we want to try the I mean solve the problem with the logarithmic n time complexity, right? In that case we can go with a segment tree, right? So we will be making use of the segment tree here just to maintain prefix sums of dp of 0j for j less than I, right? So now what we'll do, let's see the processing of each element I part, right? So I here we have I 0 1 2 3 4 compressed array we are considering, right? 1 2 3 4, right? Or we can consider 4 3, but I'll be going with this one itself, 0 1 2 3 4, right? So here compress 0, compress 1, compress 2, compressed 4 and compress 3, this one value we have to go with 0 1 2 4 3 value, right? So I will be 0 1 2 3 4, and the value for the I would be this is of the length 2 we are considering, right? So the value will be this one 0 1 2 4 3, 0 1 2 4 3. So dp of 1 0 will be 0, dp of 1 1 will be 1 2 4 4. This is after compression. This is after compression, means we are processing each element here. We are processing each element. So we got the output here 0 1 2 4 4, 0 1 2 4 4. This is fine. So here dp of 0, dp of 0 we got this one 5 times 1, 5 times 1, and dp of 1, so this is dp of 0 man, yeah, dp of 1 we got 0 1 2 4 4. After processing each I, we got the value 0 1 2 4 4, right? So let's move on with the next step here. We are done with the step 3. So now we have to build the dp for subsequences of the length 3. So we are done with the we are done with calculating for the or building dp for the subsequences of the length 2. Now we are going with the length 3, the same process, but now the length is different. The length is different. We are considering length 3 instead of length 2. That's it. The only difference is length here, right? So we are building the dp for the subsequences of length 3, right? Length 3. So I have done the calculation, so this I'll not explain. I have already explained for the this one, what do we call step 3, right? So you can just go through this one, you'll get the value, the same steps will go with the same steps, except the length is 3 here, except the length is 3, right? So this differs here. We'll get 7 and 3. Basically the dp of 2 we will get here is 00173. So this one I won't be explaining, just look into it, you'll get to know, right? So dp of 2 will be 00173, 00173, the calculation part, right? So 00173. So this one, the final answer would be, so now we are done with dp of 0, dp of 1, as well as this one, what do we call dp of 2. Nothing but first one, the initialization part, dp of 0 we got 5 ones, and the dp of 1 we got 0 1 2 4 4, and the dp of 2, now just now I didn't show the calculation part, I did this one directly because we are having the idea on this one, right? So you can just see the calculation part. So we got the output 00173, 00173, nothing but dp of 2 here, dp of 0, dp of 1, dp of 2, right? So I hope this is clear, man. I hope this is clear, right? So just give me a second, 1 second. Yeah, the final answer would be dp of 2 equals 0 plus 0 initially, 2 zeros plus 1 plus 7 plus 3. So this calculation actually I haven't showed. This calculation I haven't showed. Why we have considered here? Yeah, dp of 2, right? So this one will be, yeah, this one will be 00173. This one we are considering, I think. Yeah, this one, sorry man, so I didn't show the calculation part, right? So that's why I got confused even here. So this one will be 00173, so I got confused here. So sorry, yeah, this one will be 0 plus 0 plus 1 plus 7 plus 3. So here this would be 11, right? So but in the output we have got 7, but in the output they have given 7, right? So one more thing, while discussing the question I said we must count only valid increasing subsequences, only valid increasing subsequences. This, these two words play a vital role, right? So here in two valid increasing subsequences means we have to consider only the valid increasing numbers, right? So accordingly with the subsequences part. So here now total valid subsequences of length 3 would be this thing: 1 2 3 1 2 4 valid ones. I have I'm showing you this one directly. I'm showing you this one directly. Basically we are getting 11 subsequences which is of the length 3, 11 subsequences which is of length 3, but we will be considering only valid subsequences of length 3. So these seven are valid subsequences which are of length 3: 1 2 3 1 2 3. It is in the increasing order, right? So this is valid increasing subsequence. Next, same thing goes with 1 to 4, 1 to 5, 1 3 4, 1 3 5, 1 4 5, and 2 3 4, right? 2 3 4. These are the 7 valid subsequences of length 3. These are the 7 valid increasing subsequences of length 3, right? So total we got here is 7, and this is the uh, answer that we got. The final output is 7 here, right? So the final output is 7 here, right? So the output that we got here is 7, which is equivalent to the output that they have given for the example 1 within the question, right? So our output matches with the example output that they have given in the question. So our approach works absolutely correct in this case, right? Our approach works absolutely correct in this case, right? Now as we are completely familiar with the approach, let's do one thing. Let's discuss the complexities part, right? So what would be the time complexity here? The time complexity would be big of k into n into log n, big of k into n into log n. So why it is k into n into log n, right? So here for each of the k plus 1 lengths, we have to go with the k plus 1 lengths that they have given in the question, right? So for each of the k plus 1 lengths, we are processing n elements. We are processing n elements, right? So n we have been given 5. In our example, the example that we took, first example, n we have been given 5. See here, k we have been given 2, right? So n we have been given 5 basically, right? So for each of the k plus 1 lengths, we process n elements, and each query or update on the segment tree takes big of logarithmic n. That's what I screamed, right? So each query, processing of each query or update on the segment tree takes big of logarithmic n, big of logarithmic n. We know this one, right? That is the reason we basically make use of the data structure segment tree. If we are going with the segment tree, Fenwick tree, the only reason we'll be going with them is because we can solve the problem within big of logarithmic n time complexity, right? So here for each query or update on the segment tree, it takes big of logarithmic n. And for each of the k plus 1 lengths, we are processing n elements. So overall time complexity would lead to big of k into n into logarithmic n. Big of k into n into logarithmic n, right? So what would be the space complexity here? What would be the space complexity here? The space complexity would be big of k into n, k into n, because we will be making use of dp of k plus 1 into n array. So this you'll get to know when we write the code, man. Dp of k plus 1 into this one k plus 1 n size array. So this we'll be making use of, plus one more thing, we'll be going with a segment tree of size 2 into n, size 2 into n. Usually we'll be going with a segment tree of size 2 into n, unless for certain problems we'll be going with 4 into n as well. For the safer side, we'll be going with for some particular problems. If you are usually if we make use of the lazy this one lazy segment tree or the segment tree with lazy propagation, uh, usually based on the problem, this one based on the problems and the constraints, we'll be making use of 4 into n sometimes, or usually we'll be going with a 2 into n itself, right? So now we'll be making use of the dp of k plus 1 n size array, and also we'll be making use of the segment tree of size 2 into n, segment tree of size 2 into n, right? So here for that purpose, overall space complexity would lead to big of k into n, big of k into n. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of k into n into logarithmic n and big of k into n respectively, right? So big of k into n respectively. So now we are completely familiar with the approach and the complexities. As we are completely familiar with the complexities and the approach, we are good to write the code. Let's start writing the code. Let's start writing the code. So let's start writing the code here. Now we'll be making use of the different utilities. So I'll just import utility package here. So I'll just go with util dot star. So this is fine. So next, let me go with the class name main here. This is fine. So within this class, what I'll do, let's make use of the segment tree. Let's make use of the segment tree, as I've said, just to perform the range sum queries and point updates, right? So I'll just go with static class segment tree, right? So within the segment tree class, what I'll do, uh, we have to initialize tree and we have to initialize size. So I'll just go with a long tree. Also, let me initialize size as well. Size will be going with a this one, right? 2 into n array. So we know this one from the approach. So this is fine. Let me come to the initialization part or constructor part here. So this one segment tree. So I'll make use of the parameter n here. Only thing that we need here, the parameter n. So we have to find the smallest power of 2 greater than or equal to n for the tree size. So let me assign size to 1, and also let me write the simple while loop here. So while size, if it is greater than n, then let me make use of the right shift operator 1, right? So we are just assigning this one size to 1, right? So this is fine. We are done with the smallest power of 2 greater than or equal to n for the tree size, right? So now we have to create the tree of size 2 into size. This we had discussed in the this one, what do we call that one, complexities part, right? So in the space complexity, while discussing the space complexity, so this I'll just give tree equals new long of within the array. So I'll just go with the size into this one, we have to go with the 2 into size, right? 2 into size I can just represent this way, represent this way, right? So this is fine. Left shift operator, we are just going with a left shift operator. So this is fine. Let me come out of this one entirely. Now, as I have said earlier, so within the segment tree class, so whatever the custom segment tree class we are writing, right? So within that segment tree class, we will be going with the two methods. One is update and another one is query. One is update and another one is query. First, let's go with the update method. In the update method, what we're gonna do here, so we will be adding the value at index. We will be adding the value at the index, right? So here I'll just go with the void update. So the parameter I'm going to consider here as, so this one will be index and value. So so this will be long actually. So value will be of the type long. So within the update method, first we have to move to the leaf node. So this will be index equals index plus size. This is fine. And also let me go with tree of index. So this is gonna be tree of index plus value. So value, the parameter that we have considered, right? So now we need to update the ancestors. Within the update, usually we are gonna update the ancestor. So let me make use of the while loop here. So while index greater than 1, then let me make use of the right shift operator here again. So we are updating the ancestors, right? So then we have to merge nothing but here tree of, so let me give index here. This one will be tree index again. This has to be left shift operator man 1 plus for the right one, we will be going with the right node, we'll be going with a tree of um, index. This will be again left shift operator 1 1. This is fine. Let me come out of this one entirely. Now we are done with the update method. Update method is simple, right? So now let's go with the query method. Nothing but range sum query. This is nothing but range sum query. What we are gonna do inside the query method, we will just go with the sum from left to right. That is inclusive. That is inclusive. We are gonna go with the sum from left to right. That is inclusive. So I'll just go with long. Uh, this will be query, so let me go with int left comma and right. So this is fine. So within this method, so let me initialize sum to 0. Let me initialize sum to 0 and let me go with left equals left plus size. And also we have to consider right node as well, right, for the querying. So we have to consider segments, left segment and the right segment both, right? So right, I'll just go with right equals right plus size. This is fine. The next step, let's go with the we are going with a so we will be going with a binary search. So this will be while left less than or equal to right. So let me write the simple if condition here. If left is odd, then so I have made use of the this one man again a bit manipulation as well for this particular problem. So instead of writing this one clearly, so I have made use of the right shift operator, left shift operator, pure bit manipulation. You can just go with a left plus right by 2, those things, right? So I can just go with it directly. So I have made use of the bit manipulation because it saves the time. It saves the time. Also, this one, the code will be faster basically, right? So that is the reason. Usually for the low level code purpose, we'll be going with the bit manipulation, right? So whether using and whether you using or, right, in the place of left plus right by 2, we can just make use of the right shift operator 1, right? So those kind of things I'm making use of within this particular code, just for the this one, just for the sake of optimization and to save the time, right? So I'll just go with here, if when the left is odd, I can just write it in this way, left ampersand 1. So if this is equal to 1, so let me open one more parenthesis here. If it is equal to 1, then sum will be sum plus tree. So we are going with a left, right? So when left is odd, basically we have to increment the left, nothing but left plus plus. So let me copy the same thing and make the necessary changes for the right. So I'll just copy this part. Let me paste this one here. So this one will be right ampersand 1. This remains same. Instead of the 1, if it will be 0, if it is equal to 0, then we have to go with the right. Means we are going with the right when the right is even basically, right? So this will be sum plus, instead of this one, we have to move from right to left. We have to move from right to left. When right is even, we have to move from right to left, right? So I have to decrement the right part. This is nothing but right minus minus. So this is fine. We are almost done. Left, we have to increment the left, nothing but right shift operator 1, and the right, this one again right shift operator 1. So just give me a second here, right shift operator 1. So this is fine. Finally, we have to return the sum. We have to return the sum. So I have considered sum, right? So just give me a second here. Me, why this is not showing? A return is showing. We are updating, we didn't return anything, so we don't have to return anything within the update, I think. Yeah, we don't have to return anything in the update. So yeah, that was it. That's why it was not showing in the suggestion. So I'll just go with the return sum here. So yeah, we are done with the query part. We are done with the query part. Just give me a second here. Did I miss something? Somewhere I have missed something. I don't know what I have missed. Somewhere I have missed something. 1 second. So this one's static class segmentary I have considered. Oh yeah, this one I have closed the bracket here itself. So this bracket, so we are going with the end basically. That is the reason we were getting this one. Uh, this is showing weird basically. So let me come out of the query method. Let me come out of the query method. So next I'm gonna go with main method, right? So I'll just go with main. Here this is fine. Let me remove this one. So what happened to this one? Just give me a second, man. Here. Yeah, this is fine. Within the main method, first thing is we'll be going with a scanner. Scanner. So I'll just go with scanner itself. New scanner. This one. System.n. Just go with system.n. Also, we have to read n and k, right? So in the input, we have been given n and k in the first line, right? So n is nothing but the array length. So this one will be int array. I'll just take the full name array length here. So this one will be scanner. Oh, this is not capital S, man. I have considered variable scanner. This one scanner dot. So this one will be next int, right? So we have to move to the next integer. So this one will be int subsequence subsequence length subsequence length. So this one will be scanner again, scanner dot next int. So this is fine. N and k, we have read n and k and n and k successfully. Now we have to go with the uh, input array as well, right? So input array we have been given in the first example. They gave 1 2 3 5 4, right? So we have to consider the input array as well in the input. So just go with the array here, input. So let me completely give input array. This will be equals new int of array length, new input of array length, right? So this is fine. So the next step would be let's go with a tree set here. uh, we will be going with the tree set just for the sake of we need to sort and remove the duplicates, right? So we need to sort and remove the duplicates for coordinate compression. So for that reason I'll be making use of the tree set. So this one integer. So let me go with, so this I has to be capital, man. Just give me a second here. So I'll just go with unique values. So this one will be new tree set. So this is fine. The next one is, let's go with the iteration part. So this will be I equals 0, I less than array length. So I plus plus, this is fine. So within the for loop, we have to read the each element AI. We have to read the each element AI. So I'll just go with the input array here, input array of I. Let me assign this one to scanner dot next int. So this is fine. The next step would be unique values. So this one will be unique values dot add. This one will be input array of I. This is fine. We have this one, line number 47. We are just reading the each element ai, and in the line number 48, unique values dot add, whatever I have written here. This one we are just adding to the tree set just for the sake of sorting, right? So just for the sake of sorting, let me come out of this one entirely. Next, what I'll do, let's go with the coordinate compression. Let's go with the coordinate compression. Nothing but we have to map the original values to 0 1 2 3, because this one indexing starts from 0, right? So indexing starts from 0. So let's go with the coordinate compression. I'll be making use of the hash map, right? So we have to map the original values to uh, index particular index, right? Zero based indexing, basically it starts from 0 to n minus 1. So that is the reason we'll be going with the key value pair. We have to map that one, right? So this is nothing but the coordinate compression. So let's make use of the hash map for that. So this will be integer. This we have discussed in the approach clearly. So I'll just go with integer. So again, this I has to be capital Y. So this is fine. Let me consider coordinate map. Coordinate map, right? So this one, new hash map. New hash map. This one syntax. This is fine. So next line, let me go with compressed index. Let's initialize this one to 0. The next step is let's go with the for loop. So this one will be individual value of unique values. So within the for loop, what I'll do, I'll just go with the coordinate map. So dot again, let me go with put. So this one will be value comma compressed index. So this one will be compressed index. So let me make this one capital I. So somewhere I have given compressed index, where I have given compressed index. Yeah, so let me make this one, I have initialized here itself, right? So let me make this one capital I. So this I have to increment compressed index, right? So this is fine. We are done with the iteration part as well. So next, let's go with a compressed array. So I'll just go with compressed array. Let me go with compressed array. This is fine. Let me initialize this one to new, and so this will be of the length of the array. This is nothing but the length of the array. Again, let me go with a simple for loop. This will be I equals 0, I less than, we have considered array length, right? So length of the array, let me increment the I. So within the for loop, we have to replace the original with the compressed, this one, what do we call, uh, compressed one, basically, right? So we have to replace the original with the compressed one. So let me go with compressed array. This one equals coordinate map. This is fine. Coordinate map dot get, uh, input array of I. So this one input array I. This is fine. So let me come out of this one entirely. So let's go with the DP, right? Let's go with the DP. So this will be DP length, I. So this one will be equal to, let me do one thing. This is not required here, I think. So this one DP of length equals number of subsequences of length, right? So this, first let's initialize the DP man. So let me do one thing. DP equals, long, we are at the, this one initialization of the DP, nothing but the second step, if you remember, right? So this will be subsequence dot length, sorry, subsequence length plus 1, right? So also we have to go with the array length, right? So we have to go with the array length. This is fine. So let me go with the simple for loop here again. This will be int I equals 0. We have to consider array length. So this will be array length. So this will be I plus plus. So this time what we need to do, we have to go with the base case, nothing but every element forms a length minus 1 subsequence, if you remember, right? So this will be dp of 0, and I, let me assign this one to 1. Simple, right? Now we have to go with the, building, building part, right? So if you, build part, sorry, the building, so build part, so build, means we have to build DP using the segment tree for the fast prefix sums, right? So this is just for the sake of optimization. So as we have the trait constraint, we are going with the trait constraints, we are going with the segment tree for the fast prefix sums, right? So we will be making use of the DP to build, we have to build DP using the segment trees for fast prefix sums. Just give me a second here. So let's continue now. uh, Let me go with the iteration part. So this is nothing but, let me initialize length to 1 and length less than or equal to subsequence length. This is nothing but the subsequence length. Let me increment the length. This is fine. So within the for loop, what I'll do, I'll just consider the segment tree. So we will be making use of the segment tree, as I've said, right? So I said this one earlier, we have to build the DP using the segment tree for the fast prefix sums, right? So for that purpose itself, for the prefix sum, part itself, we are making use of the segment tree here. So this will be, this is not showing in this suggestion. Yeah, segment tree. So I'll just go with the segment tree itself. So I'll just change this one, variable capital S to small s. So this one will be new. So we are going with the custom segment tree, right? So segment tree class, we have already written that one. So this will be new segment tree of, so we have to pass array length here. This is fine. So let me go with one more iteration here. So int I equals 0, I less than array length. So this one will be I plus plus. So this is fine. So within the for loop, what I'll do, let me initialize current compressed value. So this one, current compressed value. So we have already mapped, we have already went with the coordinate compression, right? So let's go with the current compressed value. So this variable name will be suitable here. So let's do one thing. This will be, we have already made use of the compressed array, right? So let's assign this one to the compressed array of I, individual this thing, iterated value of the compressed array, basically, right? So this is fine. Let's go with a simple if loop here. I mean if condition here. So what if the current compressed value sorry, if current compressed value is greater than 0, then only we have to count all the dp, right? All the dp len minus 1 j where compressed of j less than compressed of I. So this one let me write rather than saying it. So I'll just go with current compression. So this will be current compression or current compressed value. This one, current compressed value. So if it is greater than 0, so why it was not showing in the this one? I've made use of this one, right? Yeah, now this is showing. Yeah, uh, this has to be, we have to count, right? So this will be dp of len I. So this one equal to segment tree variable I have to consider s is small man. So this is fine. Segment tree dot. So we will be going with a query. So we have to count all the this one dp of len minus 1 j, right? So this one I'll be going with a query. We have already written the query method, right? So I'll just make use of the query method here. Segment tree dot query. Uh, the initially we have to start with 0. So current compression value, compressed value minus 1, the last one. So the last value. Right, so now we have to update the segment tree for the future queries. So we'll be making use of the update method here. So this will be segment tree dot update. Update is nothing but we have already written the update method here. This one I'm speaking of, right? So this one will be segment tree dot update. This one will be current compressed value. This will be dp len minus 1, len minus 1. This one will be I. This is fine. This one will be I. So sorry, did I miss anything? Update I'm going with, right? So this one will be current compressed value command dp of len minus 1 I. Yeah, this is correct. This is fine. Let me come out of this one entirely. Now we are left with only this thing. The last part is we have to sum all the dp of ki. We have to get the total number of subsequences of length k plus 1, right? Accordingly with the question. For that one, we have to sum all dp of ki. So I'll just go with long total subsequences. This one equals 0. Uh, Again, for int I equals 0, this one will be I less than array length. So this one will be I plus plus. uh, this is fine, man. We are going with a for loop, right? So I'll just go with the total subsequences equals total subsequences plus dp of subsequence length. This one will be subsequence length I. I. So this is fine. Let me come out of this one entirely. So this is nothing but s out. So instead I have to give println here. So this is fine. System out println. What we need to print? We need to print the final answer. Final answer is in the total subsequences, right? So we have considered total subsequences. This one. Let me copy this one and let me paste it over here. So we are done with the problem. We are done with the coding part. We are done with the coding part. So let me do one thing. So before checking the code with different inputs, let me copy paste the signature starter template, right? So just give me a second here. So I'll just come here. Let me paste it over here. So this is fine. So just ignore this one. Let's concentrate on the logical part. So I'll just come here. So let's try the code with different inputs, man. So this one, I have to get the, we have to get the output 7. So let me paste it over here. So we are getting the This one, right? What? So this one has to be capital I, not the small I. Line number 59. Where is it? 59. This one has to be next int. This is fine. Here also I have to make this one capital I. We run this one again. So few errors. We have three more errors, right? So what is it saying here? Error cannot find the symbol. Why? Just give me a second here. Mm, where is it? Line number 63. This S has to be capital, man. Mm, yeah, reset. We are making use of reset, right? So S has to be capital. So let me run this one again. So now we are left with one error. Again, this I has to be capital. Line number 65. Let me make this one capital I. So if I run this one, yeah, missing return statement where line number 41. 41, yeah, for the update, we are not going with a return, bro. We are not going with a return for the update, basically. So we are just going with the parameters index and value. So index equals index plus size. This is fine. Tree of index value I have given. While index greater than 1, then we are going with the index right shift. This one, this is fine. Tree index equals tree index left shift operator 1. Did I miss any other thing? No, right? So we are not going with any this thing. What do we call? A return method. So did I miss any other thing? Bracket something. So this is also fine, right? Query is also fine. And segment tree part is also fine, I think. So segment tree, we are this is nothing but the constructor part, man. Initialization part. Size equals 1 while size less than n. Size this has to be actually left shift operator, not the right shift operator. Um, this is fine. So we have done something wrong. Just give me a second. So yeah, let's do one thing. In the line number 30, so this has to be size less than n, not size greater than n. And also V, capital V I have given here for the line number 34. That is the reason it is giving us the missing return statement, I think. So I'll just go with a small v here. So now this has to work. Let's see. Yeah, we are getting the output 7. So the output that we need to get here is 7 and we are getting the correct output, right? So let's do one thing. So those were the mistakes actually. Here this one size, it has to be less than n, and here we have to make use of the left shift operator, not a right shift operator, right? And this has to be small v, not the capital V. That was the reason we were getting the this one return statement this one expected, right? So now let me copy this one entire code. We have only one input, right? So this one, yeah, this is fine. Let me come here, let me paste the entire code and let me hit the submit button. I hope this works for all the test cases, man. Let's see. So, and one more thing, this is going to be the last problem on the segment tree, right? So next, from tomorrow, we'll be solving the problems on the Fenwick tree. The next 6 problems is gonna be it's gonna be on the this one, what do we call, Fenwick tree or the binary index tree, BIT, right? So then after solving the problems from the BIT or the Fenwick tree, we will be solving the problems on sparse table, the last 3 problems, right? 6 problems on this one Fenwick tree, 6 problems we have already solved, this one including today's problem. We have already solved the 6 problems on segment tree. Next it's going to be this one, we are going to solve on Fenwick tree, and the last 3 problems it's going to be on sparse table, right? So 15 problems we'll be solving basically. So now we are done with the problem. So we got the verdict, this one accepted, right? So whatever the code that we have written works absolutely correct for all the test cases, right? So we have made use of the segment tree bit manipulation along with the DP, dynamic programming, right, to solve this particular problem, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.